Okay, hi again. Welcome to Chemistry 111, experiment number 12, cell potentials in electrochemistry. Our purpose is to assemble a multi-purpose microvoltaic cell and compare the reduction potentials of several different metals. Let's begin by looking at a typical electrochemical cell shown here. Well, you've got a beaker that contains a piece of zinc in it attached by a wire to a beaker that has a piece of copper in it. Now, zinc likes to lose electrons more readily than copper does, so the electrons will travel from left to right in this case across a voltmeter that can measure the cell potential over to copper. Now this wouldn't work because copper is not going to gain electrons, but if you put it in a beaker that has some copper 2 ions, that's where the reduction can take place. Your zinc will lose electrons as it does so readily, and it will flow across here and do nothing at the copper anode, right? Because it's not going to get reduced, but when it hits this solution, it will take that copper 2 plus, add the 2 electrons to it, and turn it into copper metal, which will plate out here, and you could see this getting nice and shiny and larger and clean in theory. But that wouldn't work because if you think about it, you have an imbalance of ions. You have zinc 2 plus getting thrown into solution, a metal getting turned into a salt, and at this in this beaker here, which is where the reduction's taking place, you have the copper 2 plus ions turning into copper, and so whatever that anion is, typically sulfate anions, will be generating here. So all we do is create a salt bridge so that the anions can migrate over here, the cations can migrate over here, and now you have a complete circuit and things can actually flow. One way that might simplify this a little bit is to realize that all this really is a single replacement reaction. Here's the reaction right here. Zinc plus copper sulfate, if that's your anion that you used, and you probably do, will turn into zinc sulfate there and copper, and that's it. The cute thing is that we can separate it out into its oxidation and its reduction components, and when you do that, you can get electrons flowing through a wire, almost like forming a river where you can use a paddle wheel to use it to create something useful work, because there's some energy being transferred here. And that's really what a battery does, is that electron flow is where the utility comes in, and that's used to do some work to power your iPhone, for example. All right, let's go through it in a little bit redundantly here. You've got the zinc losing electrons to form zinc 2 plus, and it's going to form copper here because the copper 2 ions pick up those 2 electrons and make copper metal. They plate out copper at the cathode. The zinc 2 ions accumulate at the anode, which is not good, but if you have a salt bridge, you can just have those anions coming in there as needed. Similarly, you can have cations replacing the copper 2 plus ions, so the salt bridge is key. Here's the overall single replacement reaction. The net ionic equation is that zinc gets oxidized, copper gets reduced. The voltage can be calculated using standard reduction potentials and flipping around the value of whatever got oxidized, which in this case is zinc. And you take the cathode minus the anode, which is plus 0.304 for zinc, and we subtract the minus 0.763 for the copper, and you get a total value of 1.1 volts positive. That's a 1.1 volt electrochemical cell. Now what we're going to do is we'll construct something that can do far more than that. We can have our copper right here, but we'll also use 3 different metals, and we'll begin by comparing the zinc, the iron, and the silver metal. So we'll construct a microvoltaic cell that looks like this. You've got copper ions always being reduced to plate out copper. So that's always what the reduction reaction is. And we just make sure that we have salts that can migrate here. As long as this is wet with some kind of a ionic compound, we should be good to go. And so the net reaction will always be copper 2 plus plating out copper here. And the things that we're going to compare their ability to be oxidized, which means their reduction potential, is silver, iron, and zinc. So silver would turn into silver 1 plus as the copper 2 plus got reduced. Iron, because silver never really forms a plus 2 ion. Iron 2 plus Iron will turn into iron 2 plus and will reduce the copper 2 plus, and zinc similarly will form zinc 2 plus. That's this reaction right here, and it will reduce copper 2 plus. So here's the net ionic equations for each of the three of these. And here's our procedure. We're going to log into Evil Logger Pro, and we'll fire up the experiment 28 microvoltaic cells. These are all Vernier labs in case you haven't noticed by now. We'll create the three-way microvoltaic cell as indicated. This is filter paper. You have some salts going here. You draw this and you actually put little pieces of each type of metal right on that spot right there. So once it's assembled, follow the instructions and measure the potentials of copper versus iron, copper versus zinc, and copper versus silver. In every case, copper is the thing that's being formed, so it's being reduced from copper 2 plus. The second metal is the one being oxidized. Iron's being oxidized, zinc's being oxidized, or silver's being oxidized. And do it as indicated. We'll also measure, since we can, the other three possible ones: iron versus zinc, iron versus silver, and zinc versus silver potentials. Some handy tips is, number one, just as always, things are pretty straightforward. Just follow the instructions. You only need to touch the metal leads to the metals. You don't have to clip them on or anything like that. And it will require us sanding things down to have a nice clean metal, but please don't do it on the bench top because it tends to scratch the bench top up. So do it somewhere where it won't scratch stuff up. The calculations are two really in nature, but with a very important note number 3 here, which is 1, calculate the standard reduction potentials versus the copper as a reference. That'll be filling in one of the tables. 2, calculate the predicted cell potentials for iron versus zinc, iron versus silver, and zinc versus silver. That's also filling out a table. And that's where we come to important note number 3 here. Note that the grading is based on completing all the tables that you have to make and writing down the correct half reactions and sometimes looking up the correct standard reduction potentials. Make sure the tables match your data. That's how the grading sequence goes. There also is a little bit, as usual, of an accuracy component, but that should be pretty straightforward since this doesn't look too difficult to build. Complete those post-lab questions, and this is the last real lab we'll be doing. After this, we have one quickie lab, I believe, to wrap up the semester. Okay, enjoy chemical reaction number 12.